Yayındayız hocam. Hocam yayındayız.
Good afternoon. Today is the second day of the undergraduate academic conference organized by Turkey section, IEEE Turkey section, and today is the second day, and we have now in the fourth session we have 6 papers and as well as a keynote speaker. I would like. Good afternoon. And I would like to welcome. Today is the second day of the. I'm sorry. Let academic conference organized. So I would like to welcome Dr. Tankut Barış Aktemur, and he's going to present Data Parallel C++. That's the title of his talk. And let me also give a little biography of Barış Aktemur. He's actually working as a senior software engineer at Intel Munich. Previously he was an assistant professor in computer science at Özyeğin University, and he received his BS degree in computer engineering from Bilkent University and master's and PhD degrees in computer science from University of Illinois Urbana-Champaign in 2005 and 2006 respectively. Research interests include programming languages, compilers, debugging tools, and software engineering. So I would like to welcome Dr. Barış Aktemur. Barış, I'm very happy to have you here. So I believe it's going to be a very nice presentation, and the floor is yours, Barış.
Thank you very much, Hocam. It's a great pleasure for me to be here. So I would like to thank you for the invitation. So you already presented my background, and I had actually prepared a slide that explains my professional background in 4 pictures. So what I would like to talk about today is data parallel C++ within Intel's One API. So let me begin by explaining the problem here. So in computer science today, a major problem is that the modern compute workload is diverse. So there are many problems in expanding to a wide range of domains like artificial intelligence, data analytics, video and graphics. There are engineering applications, applications in economics, and so on. But these problems have to be solved in an optimized, power efficient, and scalable way. So this requires that that we solve these computation requirements using a variety of hardware. So sometimes with a CPU, sometimes with a GPU or an accelerator. And programmers have to use a variety of software components, like there are different programming languages, various APIs, tools, and libraries. So this creates a complexity in the way that developers can approach or address these problems. So one API is an initiative, a very large initiative by Intel. And the goal here is to provide the programmers with a unified programming model so that they can deliver uncompromised performance across multiple architectures. So to illustrate this, what programmers want is optimized applications. So these optimized applications will be running on CPUs, GPUs, or accelerators. And one API provides the thing that's here in the middle, the big blue box. This box presents the contents of one API-based toolkit. And by running applications on one API, the goal is that the users will be able to utilize a variety of architectures in an optimized way. So the base toolkit contains things like, for instance, gives the ability to do API-based programming. What this means is that there are here components such as the math kernel library, or there is threading building blocks, or there's a deep neural network library. So using these libraries and the API that the libraries provide, the users can implement solutions for their problems. And it also provides analysis and debugging tools such as vTune, Advisor, and Intel's distribution for GDB. So there are several other toolkits too. So here I just gave the base toolkit as an example. And another thing that the base toolkit contains is the direct programming model. The direct programming model means users can take advantage of what one API provides by directly coding, developing software for their applications. And the key part in the direct programming side is data parallel C++. So this is what I will be talking about first. So data parallel C++ or DPC++, in short, is actually we can say that it's a language API that supports data parallelism and heterogeneous programming. So it allows the programmers to reuse code across hardware targets, ranging from CPUs, GPUs to accelerators. And I would like to explain it through a sample problem. This is vector addition, and this is a very, I mean, for presentation purposes, I picked this simple application. It's a data parallel problem. It's actually embarrassingly parallel, and there are. But I would like to say that there are many other and real world samples available at the link that's shown on the slide. But vector addition is, I think it's going to provide us a good introduction. So the problem is in vector addition is we have actually, let me try to switch to laser pointer. Yeah. So the problem is that we have two vectors, the input 1 and input 2, and these arrays, array of elements are processed. So the elements are summed up together, and the sum is written into the output. So if we were to address this problem sequentially, then the solution is very straightforward. We iterate through the data, and then we process for each data point. So we add up the elements and write the result back to the output vector. So this would be how we process data, and this would be the way, on the right-hand side, this would be the way how we process one data item. So for the purposes of presentation here, I deliberately wrote this example a bit in a verbose way. Of course, you could have written this with a single line inside the for loop, but I wanted to make the approach here more clear, that we are processing a single data element in this case. So if we run this application, again, note that this is sequential, so there would be only one thread. It would work like this. So the thread would go over the elements one by one, and then it would write the output to the output array. Now here's how the same problem can be addressed by data parallel C++. In this case, the function that processes the elements is exactly the same, but the way that we use this function is different. So in this case, we would first create a queue. A queue is where we submit commands that will be executed on the target device in parallel, I mean concurrently. So the target device could be a CPU, GPU, or an accelerator. And we then need to just create and initialize the data, and then we specify the data range. In this case, we specified that it's a range, a one-dimensional range of size, many elements. And then we basically submit a command to our queue. And in this case, the command that will be run is a parallel for. So we don't have an explicit for loop anymore. Instead, we just specify how we would be processing one data element. So what we pass to this parallel for function is a lambda, and it takes a parameter which specifies the index of the work item, and then using this index, we specify how to process the data. And then finally, we can wait on this queue because submissions are asynchronous. But if you want to wait, if you want to synchronously wait for the result to be available, we will have to just call wait. But this means that because computation is done asynchronously, we could have simply done other stuff while this parallel for is being submitted to the device and being executed. So what happens in this case is that the DP++ runtime receives the so-called here kernel. This is the computation kernel, and then it's going to distribute it to threads, to multiple threads, so that our computation is going to be executed in parallel. So here there are, of course, various ways of how the computation can be assigned to threads. Here is one possible execution scenario. The runtime could split the data range into separate chunks, and then each chunk can be assigned to one thread. For instance, here the first 4 elements could be assigned to thread 1. The second range of 4 elements could be assigned to thread 2, and so on. And again, this is just a possible execution scenario. Threads could be processing their elements, the assigned range of elements, sequentially. So in this case, when we run the runtime, the execution would look like this. Another possible execution scenario is, so suppose threads have vectorization support, or in other words, this is SIMD, single instruction multiple data support. In this case, threads could be processing multiple elements at one time. And so threads could, instead of iterating through the data elements sequentially, they could simply process them again in parallel. So in this case, if we execute, the execution would look like this. Okay. So how the assignment of threads to data ranges and how they could be vectorized really depends on the devices that we have available on our system. And also, the nice thing here is that this is done by the SQL runtime. So the programmer, if they want to, the programmer can just stay away from it. Yeah. But of course, Data Parallel C++ gives the ability to fine-tune how this assignment could be done. And this will actually be required in real-world cases in order to get the best performance out of the hardware. A very nice property of DPC++ is that it allows us to conveniently offload kernels to a variety of architecture, CPUs, GPUs, FPGAs. And the thing is that the code that I've shown you, without, almost no change, actually the code that I've shown requires no change at all, can be run on CPU, on GPU, or on with some changes on FPGA. So this is a great convenience for developers, because they could try out their application on CPUs or GPUs, and this really helps improve the software development cycle. Data Parallel C++ is actually standard C++ plus the SQL standard. The SQL standard is an open API specification from the Kronos group, and DPC++ adds some community extensions on top of that. And the code actually is standard C++. That means I could actually run the code using a compiler that does not even know what DPC++ is. So I've talked about Intel's DPC++, but there are other SQL implementations for several other hardware. Actually, if I go to, let me try this. For instance, this is the link that was on the slide. If you scroll down here, you would see things like, well, there's Intel's One API, and then there is a Compute CPP from CodePlay, which targets, for instance, NVIDIA GPUs, AMD GPUs, and so on. There is an implementation from Xilinx called Tricycle. There is Hipsicle from University of Heidelberg, which can target any CPU, NVIDIA or AMD GPUs. And then there is NeoSQL implementation from Tohoku University, and so on. So it's an open standard, gaining substantial interest from the community. It's an alternative to single vendor proprietary languages. And I'm not going to name any names, but when I say a single vendor proprietary language, I believe it's clear what is meant. It's possible to try out DPC++ using Intel Dev Cloud just for experimentation, or there is Data Parallel C++ book. Both are freely available. So that was the part where I introduced DPC++. And if I go back to this big picture, on the right-hand side, I also said that there are analysis tools. And one tool here is Debugger, and that's based on GDB. And I would like to now talk about the Debugger. And I would like to, my job, my position in Intel is about developing the Debugger. So I made contributions to this Debugger. So that's why I would like to use this opportunity to also present it. And I would like to start with a demo, and then I will present how the debugger works. I mean, the internal architecture and the mechanism. So let me switch to my terminal. This is the code that I gave as an example, the vector addition. Here's the main function. We create a queue, and then we create the data arrays, input 1, input 2, output. And these are created using something called the malloc shared. This actually comes from a feature of DPC++ called unified shared memory. So the memory allocated this way can be migrated between CPU and GPU memory seamlessly with the help of the DPC++ runtime. So this happens transparent to the programmer, so it's very convenient. And then we initialize input arrays. So input 1 is going to have even elements, and input 2 is going to have odd elements here. And after allocating and initializing data, we simply call the function that does the addition operation in parallel. And this is the function. It's the thing that we saw on the slide previously. So it takes the queue, input and output arrays, and then it calls parallel for, inside which we process each element, the given element. And the process function is simply up here. Just read the elements, add them up, and write to the output array. And I would like to just give a note here is that the code that I show here does not contain any error or exception checking. I simply omitted them to keep it clean and simple. So it's only for demo purposes. So that's the code. I already compiled it, and I would like to now start this. Let me try to. Okay, so I would like to now start this using the debugger, and I'm going to define a breakpoint. The breakpoint that I will define will be inside the kernel. So let's use this line. This is line 51, shown here. and then I run my program. So the program runs, and then it hits the breakpoint. Yeah. And now at this point, I can inspect my program. Inspect meaning I can print variables and so on. And note that the debugger here prints some informational messages. Like, for instance, it says that we have attached to device 1 of 1. So on the machine where I'm running this demo, there's only one GPU device. But it's possible that I had multiple GPUs as well. And then the breakpoint hit comes from thread 2.1. So if I do info inferiors, what I will see is that I have two inferiors here. And inferior in GDB terminology means basically the process, the debuggee, the process that we are debugging here. The first one is the host process. This is the process that actually offloads the computation to the GPU. And the second one, with this description, device 1, is the thing that represents the code that's running, the kernel that's running on the GPU. So I received the breakpoint event from thread 2.1. So the prefix, the 2 dot part of the thread ID actually refers to the inferior ID here. So this basically means that the thread is the first thread of the second inferior, which is the GPU. Okay. And now I'm actually inside the GPU. And if I do something like, for instance, disassemble, what I will see is GPU instructions. I can switch to, let's say, just to show you that we are actually inside GPU, I can switch to inferior 1. This is the host application that runs on CPU. And if I do disassemble, now I will see x86 code. Let's go back to the GPU. And now let me do info threads, and I would like to get information of threads from inferior 2. So these are the GPU threads. And here I see that there are 4 threads. The first one is split into 2 lines. And the reason is this. So threads on GPU are vectorized. So vectorization means they have lanes, SIMD lanes, and each lane, those lanes are executed by the thread in a lockstep motion. So they one instruction impacts all the lanes. So the current lane, the lane that is that defines our context is lane 0 in this case. And these are the other lanes that are available. For instance, if I take a look at thread 2.3, it also shows me that there are lanes from 0 to 7. So in debug mode, GPUs have 8 lanes. But there's something special about thread 2.2, and it is that it has 6 lanes, not 8. And this is a deliberate thing that I did. If I go back to my code, we will see that as the size, as the number of elements, I used 30. So I deliberately didn't use an exact power of 2 in order to show you the impact on the lanes. So the thread which was assigned the last chunk of the data range here was assigned only 6 elements. So the other, so the last, for instance, last 2 lanes of this thread is disabled in this case. All right. Now let me open the text user interface mode, and let me make up some space here. Or actually, before that, I would like to show you one more thing. So our current thread is at this line where we defined the breakpoint, and this function process is called from inside my kernel. Now you can do standard, I mean the usual debugging activities like printing the backtrace. So the first frame is processed, the second frame is at par. Or you can do, you can go up in the call stack or down in the call stack and so on. Now let me make up some more space in my command line. That seems better. Okay. So for instance, I can do step over. I can run one line of statement in my code. Also one of the popular commands when people do when people use when using the debugger. So the thing is, now I have multiple threads, but when I resume a thread, I would like to resume only my current thread, and I would like the other threads to stay at where they are. I don't want to resume them. And the way to do this in GDB is to set the scheduler locking configuration to, I will use the step mode. And then if I do a next, my current thread is going to execute the current line. It will go to the next line. But if I do info threads, again, the GPU threads, so I use 2 here as the inferior ID. And now I see that my current thread, 2.1, is now at line 52, whereas the other threads are still at line 51. They are still sitting at the breakpoint. And we can print elements, print variables. For instance, there is element 1 here. If I do print element 1, I will get the value, or print element 2. So the value that's being printed here is defined according to our context. And the context here is that we are inside thread 2.1 and SIMD lane is 0. So the elements are printed here according to the also to the current SIMD lane. I can switch the lane. For instance, I can switch. I can go to lane 5, and if I now print element 2, now this is the value from the point of view of lane 5. Let's go back to threads lane 0, and another way to see vectorization is this. I can do thread apply command. The thread apply command applies a given command to each thread or each lane. In this case, let's say that we want to apply to all lanes, to all active lanes, this command of printing the element, printing element 2, and here we see that on this lane the value is 1, on lane 1 it's 3, lane 2 it's 5, and so on. So these are the odd elements. Or we can actually, in order to show that the data here is in fact vectorized, I can use the examine command. The examine command is for examining the memory, and here I would like to examine the memory. I would like to actually display 8 elements because I have 8 lanes, and each element should be displayed using the decimal format, and each element here has word length, And the address that I would like to examine is element 2. And here I see that these values are actually organized side by side in the memory. So this shows vectorization in effect. And if I do the same for element 1, I see that these are even values. So let me check my notes. All right. So if I now continue, I can resume my program. So suppose I did my inspection. I want to resume my program. And now thread 2.2, another thread hits the breakpoint. Let's continue. And okay, before I continue, I would like to also define another breakpoint at the end of the program beyond the kernel. So let's define a breakpoint here at line 78. So break 78. And let's resume again. So I hit breakpoint on thread 2.4. So I had 4 threads, and this is the last GPU thread. And if I resume again, now the breakpoint hit comes from thread 1.1. So the inferior one was representing the host part of the computation. So the kernel is complete, it's finished, and now we are back in the host, and the debugger can do this switch seamlessly. Now we are inside the host, as denoted by info inferiors. Now our current inferior is inferior 1, the host process. And here I can again do inspection. For instance, I can print the value in input 1, index 12, or input 2, or output. So now the values that are being printed here are from CPU and CPU memory. Yeah. And let's resume, and the program terminates, and the inferior that represents GPU now has been removed. Okay. So this shows how one can do debugging on GPU, I mean inside a GPU kernel. So what is fortunate for us, I mean for us debugger implementers, is that some people tend to use printf statements, and they avoid using the debugger when they are debugging CPU applications. But if you have to debug the GPU, well, printf approach does not really work there. So you have to use the debugger. So I mean that's our luck. So this was the debugger demo, and now I would like to talk about how things work, and then I will be done. So here is the build flow, and this is what we see here is for JIT compilation, just-in-time compilation. So we have our code. The code is compiled by DPCPP compiler, and it produces a host binary. The host binary in this case is called a FAT binary because it contains in a section what is called a spear V that corresponds to the kernel. So the compiler detects the kernel, and then it translates the kernel to an intermediate format in spear V specification. And if we use, if we enable debug info during compilation, for instance, by using the -G flag, then this PRV is going to also have debug info together with it. Then let's say we launch the application. This is going to create a host process, and then host process at the execution time is going to extract out the intermediate level representation of the kernel, and then it gives it to a device compiler. And the device compiler converts this, compiles the code down to machine code, and it converts it to actually an ELF dwarf format. And this could be for, let's say, if we are targeting a CPU, then it would be for CPU. I mean, it would be containing CPU instructions. If we were targeting a GPU, this ELF here contains GPU instructions. And those instructions are then offloaded to a CPU or GPU, whatever target the programmer picked, and they are executed there. So from the debugging point of view, it's this ELF and dwarf that allows map the machine code back to the source code. So how does a debugger work in general? So this is the view from this is the Linux view, but the same principles apply on other operating systems such as Windows too. So suppose we have an application that we want to debug, and the application runs on top of OS and executes on CPU. If you want to debug this application, you would also start the debugger. So in this case, we are using GDB. So GDB is another process that's running on top of the OS. But the OS provides an interface. On Linux, it's called ptrace. This is an interface that allows the debugger to announce itself as a tracer for this application. And when this happens, the signals that would otherwise be directed, that would be delivered to the app, are then delivered to the debugger itself, to the tracer. And through by being the tracer and through ptrace, this debug interface, the debugger can start the process, or it can peek or poke its memory. This allows the debugger to inspect the values. It's also the thing that the debugger used to insert breakpoint instructions. For instance, the debugger on x86, there's this interrupt instruction. The debugger simply writes the instruction memory in order to replace an instruction. And then when the application executes it, it will hit the interrupt and the debugger will be notified. And then the debugger can write back the original instruction in order to make the application execute the original code and so on. This allows inspecting the thread state, that is the registers. The application can be resumed, or it can be executed to run only a single instruction and so on. So this interface, these abilities are the building blocks on top of which a debugger is implemented. But what if the application is offloading to a kernel? So in this case, the host application is still there, but it has a kernel that is offloaded to the GPU. It doesn't run on CPU anymore. So ptrace works only for the host part. The kernel that's running on the GPU is transparent to the debugger, and with there's no way to in this setup, there is no way to debug GPU kernels. So the solution here is to provide the debugger an interface that is specific to the GPUs, so that the debugger can control the GPU just like controlling the CPU applications. So here is the current architecture of the debugger that I presented. So there's the host application, it has a kernel, and using GPU runtime, it JIT compiles the kernel, producing an ELF file plus dwarf, the debug information that is offloaded to the GPU. So the application is running on top of the OS, and the GPU runtime here talks to the GPU driver so that the code can be offloaded to the GPU. And then there's the debugger. The debugger inside has a native target description, which uses ptrace to be able to debug the host part of the application, the part that runs on the CPU. And then there's a GDB server. So this GDB server it knows the GPU architecture, in particular here, the Intel GPU architecture, and it contains the specification. So it knows the details of it. And it is linked with a debug lib, which communicates with the GPU runtime, so that GPU runtime is going to understand that the kernel is being debugged and will do necessary setup. And the debug library also talks to the debug driver. And through this debug driver, just like using ptrace for CPU, it's able to control the GPU. So it receives exceptions, it receives interrupts, it's able to peek and poke the memory or the state. It's able to resume threads and so on. And finally, inside GDB, there is also a remote target, which is connected to this GDB server for GT. And plus, there are definitions of Intel specific to the Intel GPU architecture. And in the demo, what you saw was like inferior 1 was this actual Linux native target, and inferior 2 was for the remote target. And this completes my talk here. So for more details, I would like to refer you to the link that's shown on the slide. There are many more information, tutorials, documentation, download links, and so on. Thank you very much.
Thank you very much, Barış, Dr. Aktemur. We actually have a couple minutes for the questions. Maybe I just go first.
Okay.
What I would like to ask you about the devices. I mean, what are the devices that currently this DPC++ supported?
So DPC++ supports, well, it supports Intel devices. Those are the GPUs. So there are Gen 9 and Gen 12 devices. So and also Gen 11. So there's, I mean, the list is kind of long. For all the details, I would have to refer you to the link. But in addition to these GPUs, there's support for FPGAs as well. But for the debugger, debugging an actual FPGA is not supported. But debugging FPGA emulation is supported.
Okay. So how about like CUDA?
Mm-hmm.
Let's say we have some code and I mean, let's say we have an NVIDIA GPU.
Yeah.
And how does the migration work? Should one start doing the coding in DPC++ and then migrate to CUDA, or what should we do? And also similar to the OpenCL as well, another question. Like OpenCL, how do we migrate from DPC++ to OpenCL and CUDA? Is it easy or is it difficult?
Yeah, that's a great question. First of all, let me go back to this SQL web page. And let me just say that if you can run SQL programs or DPC++ programs. I mean, sometimes the DPC++ is a superset of SQL, basically. You can run them on NVIDIA GPUs. As you see here, there is already support. But how do you migrate your CUDA code to DPC++? Well, there's a tool for that. I would like to go back. So here on the slide, in the direct programming box, there is Intel DPC++ compatibility tool. So this is a tool that that can assist the programmers to migrate their CUDA code to DPC++. It's not 100% migration, but you can, I mean, it assists the migration greatly. For instance, I mean, I don't want to just make up some numbers, but a great portion of your code could be migrated, and then the programmer will have to do some manual tuning and adjustments. But it's supposed to do the transition. I mean, help the transition to a great extension. Actually, at Intel, some application engineers are already using this tool because there were some existing applications, and they are actually using them to do the migration. For OpenCL, there isn't, as far as I know, there isn't a tool, but SQL originally, SQL is defined as an abstraction on top of OpenCL. So if you have an OpenCL program, the concepts are very similar, and I would expect the transition to be actually smooth, because SQL was originally designed as an abstraction on top of OpenCL.
Okay, so these companies, do they, I mean, are they willing to adopt this new methodology, the SQL?
That's my impression, yes. That was my impression.
So are they like NVIDIA, the other companies, they started moving on to this approach?
To be honest, I don't know what NVIDIA does at the moment, and I mean, whatever I say would be misleading. So I should refrain from doing that. But yeah, there are several companies that are already adopting DPC++, and also there are several academic projects as well. So this may be of interest to you, I mean, to the audience of this conference in particular. There is an academic program of DPC++, and many universities are already in transition to DPC++. The nice thing about DPC++ is that it allows the users to switch to an open platform instead of being locked into a single vendor system.
Okay, thank you very much. Those were my questions. Let
Thank
me
you.
check for the anybody else have any other question. I think we have we don't have any other questions, so thank you so much for giving us this nice speech. It was very, very interesting, especially for me. It was very interesting.
Thank you.
And
I
also
wish I could do I could show more stuff related to FPGAs.
in the future.
Maybe.
Okay, it will be very nice. So it's very nice to have you, Barış Hocam. Thank you for coming and
Well,
giving
I would like to thank you for the invitation. It was a pleasure for me.
Thank you.
Mm-hmm.
So we will join again in a couple minutes with the other presentations. We'll see you in a couple of minutes, so we have to stop now. So we'll see you in a couple of minutes for the next presentation in the session.